just do,
Yeah,
okay.
is that okay? If we
yeah,
record?
John
Oh,
Williams
John
is
Williams.
on. Yeah, great.
Yeah,
Just have to
And
say.
so this is going to be shared, for everybody, if that's okay with you, John.
Yep,
Renfeld.
that's fine.
Okay. And, what a pleasure to have you on this. A veteran of 5 shuttle missions from, I think, 1995 to 2009.
Yep.
And in the middle of all those exciting missions, you had
Thank you.
8 spacewalks. The Hubble, he's my favorite Hubble hugger. Dan Goldin always talked about Hubble huggers and all that, but I revered in the fact that I knew a Hubble hugger that worked on the Hubble. So, and then in his post shuttle mission career, he went to NASA and served as an associate administrator for space science directorate at NASA headquarters. God help him. And that's probably why he moved here to Boulder after that. He did that in January 2012. So he's a survivor of the NASA headquarters activity, and a full-time great guy, and again, a Hubble hugger that we've all known to revere. So John, take it away.
okay, you're good.
All righty. So if everyone would mute.
You have to stop.
Can you give John the screen, please?
Yeah,
All righty. I'm used to having multiple screens. You cannot start screen sharing while other participant is sharing. All right, so I should be able to do that now. All righty, let me. At some point, it should start a slideshow.
There's something came up.
All righty.
Something came up.
So if everyone would mute though. that would
yeah,
be-
or John can you? I gotta go.
I'm waiting for, yep, there we go. Barbara, if you would mute. Beauty. All right, so what I thought I would,
John, mute everybody. There's a bunch that are not muted.
I'm not sure I think, oh, you were talking to a different John.
John Williams.
Yeah. So as Leonard said, I have a particular affinity for both the James Webb Space Telescope and the Hubble Space Telescope. The Hubble Space Telescope, because I spent a better part of my astronaut career working on servicing the telescope, and then as at Space Telescope Science Institute managing the telescope before I lost my mind and went to NASA headquarters, where I managed the James Webb Space Telescope program. But the interesting thing is, and my small contribution to astronomy, I'm a astrophysicist professionally, but is that I have the distinction of saving both the Hubble Space Telescope from an early end and saving the James Webb Space Telescope from cancellation. The Hubble Space Telescope, as you know, had 4 servicing missions, and then Sean O'Keefe, the NASA administrator, in 2004 announced publicly that we were not going to go back to the Hubble Space Telescope. And that would have meant that sometime around probably 2017, we would have lost the Hubble Space Telescope. At the time, we thought it would be as early as 2007 because of its batteries, but we learned how to operate them a little better. And I thought, I understood his rationale. obviously I supported him because he was my boss. I was NASA chief scientist at the time. And I worked very hard behind the scenes to make sure that Hubble could keep going, that the contractors kept working on servicing, the instruments were being developed, so that if Sean O'Keefe was replaced by another NASA administrator, there would be a chance to go back. And the catalyzing event really was the reflight of the space shuttle after the loss of Columbia. Once that flew, then Mike Griffin had the opening to be able to say, let's go back to the Hubble. And then he asked myself and Chuck Shaw, a flight director and relatively serious amateur astronomer, to put together a plan for how we could go back to Hubble with a modicum of safety in case, you know, the foam from the space shuttle external tank hit the wing and the Hubble crew had a similar situation to what happened to Columbia, but in this case, they would stay in space and have to be rescued. As a penalty for me figuring out how to do that, Mike also asked me to go back another time to the Hubble and lead that mission, which I did in 2009. So I'll show you a couple pictures of that. So we flew the mission in 2009, the 5th and final servicing mission with the space shuttle. And that's allowed us to have a healthy Hubble Space Telescope to this day. Amazing that it's 32 and a half years old, still doing, you know, pinnacle science. And I'm really gratified that we have now both the Hubble Space Telescope and the James Webb Space Telescope. Now, the James Webb Space Telescope was started in its conceptual phase before Hubble was launched. In 1979, we were already working on concepts for the next generation, space telescope, and you know, Hubble was quite a ways away. And then in 1990, when it was launched, we were already working on the next generation space telescope in earnest. And it's taken quite a while to get it there. But when I took over at Space Telescope Science Institute as the deputy director, I started learning about the programmatics of JWST. And what's really interesting is Sean O'Keefe is the NASA administrator who named it James Webb Space Telescope, and I'll talk a little bit about that. But in 2010, looking at the way the project was being developed, I was quite alarmed that it looked like on its then trajectory that it wouldn't launch in 2014, which is what we were holding, and that it would just keep moving out and out and probably wouldn't launch until, you know, sometime in the 2020s. And that was just totally unacceptable. So we worked out a plan with, we talked to Ed Weiler, we talked to the NASA administrator at the time, Charlie Bolden. We talked to Senator Mikulski, and she agreed that that was just untenable, that we would might not launch until 2022, and which is what we told her that, you know, it looked like. And she and Richard Shelby, the senator from Alabama, asked NASA to do a study, which we had told them the best thing to do is ask a distinguished team to do a study that will reveal all of these problems, and then she could work to get an appropriation so that we might be able to launch it in 2015. Well, as it turned out, Garth Illingworth, a really wonderful astronomer from UC Santa Cruz, he's Mr. Hubble Deep Field, and one of them, and John Cassani, the systems engineer from JPL, who had worked on many JPL missions, came out and said, yeah, the program is in big trouble. It needs more funding. It needs more attention, and we can launch in 2015 if Congress can appropriate the money. They did, but they couldn't do it fast enough because the annual cycle of budgets are a fiscal year. So we set a date for October 2018 as the launch date with the budgets we had. And then I took over as associate administrator and was responsible for James Webb. And up until I left in 2016 and moved to Boulder, we were on track for a 2018 launch. If somebody really wants to know why we didn't launch in 2018, I can talk about that. But NASA lived up to its part of the bargain and delivered the optical telescope element, the telescope part, in October 2016 to the day and practically the minute that we said we would when we re-baselined the project in 2010. But the spacecraft wasn't ready, and that's the principal reason. So, you know, big picture, and that's a picture of me in 2009. The NASA mission, the way I see it, is to innovate, to create new things that allow us to explore the universe. And when we explore the universe, we discover things. And when we discover things, we inspire people in our country and the world. And James Webb Space Telescope and the Hubble, but James Webb in particular, we had to invent new technologies for a cryogenic telescope that involved mirrors, that involved structures, that involved detectors, because the whole telescope is passively cooled to about 40 Kelvin. And we'd never done that before. We had to invent a new sun shield to block the sunlight because it doesn't have a tube like a traditional telescope. And so a lot of the early work was spent innovating those new technologies, investing in those new technologies. And so now James Webb is on station at Earth-Sun L2, exploring the universe and already discovering things that I know inspire me. And hopefully I'll show you a few things that you might be inspired by. Now, I don't have any particular deep insight into, you know, what's going on other than talking to, you know, John Mather, the project scientist, and others at Goddard Space Flight Center and Space Telescope Science Institute. But almost everything is being either blogged out or reddited out or tweeted out or on the website. So first of all, this is a tale of two telescopes and a tale of two people. You know, Edwin Powell Hubble, named after his middle name, John Wesley Powell, the famous geologist, explorer, you know, is a famous American astronomer. I think you all know, we all know the Hubble Space Telescope was named after him. And we have the Hubble flow, the expansion of the universe. And he did, in fact, through observations of galaxies, discover that the universe is expanding with colleagues. Here he is shown at the 48-inch Schmidt telescope on Mount Palomar, smoking a pipe, which he never used the Schmidt telescope, and you're really not supposed to smoke pipes around telescopes. But other than that, it's a nice picture. He lived from 1889 to 1953. Now, at the time he made these observations, and this is 6 October 1923 of M31, he was using glass plates with photographic emulsion, and we didn't know these were galaxies. They were called nebulae, clouds, and you know, it was thought that these might be large clouds of gas. But around this time, he and others started to realize that these clouds of gas had Cepheid variable stars in them, which are stars that pulsate, and the pulsation time is proportional to their luminosity. And that allowed him to figure out how far away these things were. And it turned out they were ridiculously far away. And you figure out how far away they are as you measure the pulsation. That tells you how intrinsically bright they are. And then just from 1/r², you can figure out how far they are. And so eventually they figured out these were clouds of stars. Somebody came up with the clever name galaxy, and that stuck a lot better than island universes, which was an alternative. And because we have Photoshop, we can invert the colors in the image, and this looks like, you know, a traditional spiral galaxy. So he used this to discover that the universe is expanding and set himself in history. So the Hubble Space Telescope, as you know, is, you know, orbiting the Earth. It's probably at about 550 kilometers right now. It now weighs 26,500 pounds. We've added a fair amount of weight, over 1,000 pounds of equipment, new solar arrays, new instruments. It's really not a particularly large telescope. It's a 2.4 meter Ritchie-Curtienne Cassegrain telescope. It has been up for 32 years, and it's an ultraviolet to near infrared telescope. Orbits the Earth every 96 minutes, and we've been up to the Hubble 5 times. Now, the incredible thing is using the Hubble and ground-based telescopes and other space-based telescopes, we've been able to pretty much fill in the story of the universe, starting, inferring that there was some kind of Big Bang, there was cosmic inflation, and we've learned that from looking at things like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, telescopes in Antarctica. And so the energy of the universe expanded quickly and cooled. And after a few 100,000 years, the pattern of radiation was frozen into the universe. And I'm old enough to have watched static between TV channels, which is that microwave background radiation, about half of it. The other half is noise. Although honestly, when you were on a network television, I think it was all noise as well. But we were able to observe that background pattern of the afterglow. And it has been, as the universe expands, that's been cooling. And we're able to observe that now as the 2.7 degree background radiation. The universe continued to coast as the universe cooled. And eventually we had neutral hydrogen, a little bit of helium, a tiny bit of lithium, but light couldn't travel through the universe because if a photon traveled very far, it would hit and ionize a hydrogen atom and stop. And so the universe was through a period called the Dark Ages. Now, we know that a significant fraction of the universe is filled with something called dark matter, and between the atoms of normal matter and dark matter and gravity, some of that matter started coming together, heating up, and the first stars turned on. And when those stars turned on, they were probably very massive. They produced lots of ultraviolet light, and that started to ionize the hydrogen. And at some point, around 400 million years into the universe, there were enough stars to reionize the hydrogen in the universe, and suddenly light could travel again. And so that's the first point at which telescopes like Hubble or James Webb Space Telescope can start to see things. Now, we don't really know much about the Dark Ages. There are ways to probe it. And we don't know very much about the first stars and galaxies in the universe. But Hubble has given us some hints. And this is why we built the James Webb Space Telescope, is to look back to that very early time. Since then, we've been able to study the assembly of galaxies, stars, solar systems, planets, even studied, obviously, a great deal about our own solar system. And then with Hubble observations, we've seen that the universe is not only expanding, but it's accelerating. And from that, we infer that there has to be some kind of cosmic pressure, which we've called dark energy. So pretty remarkable, all the things that we've learned about the history of the universe using relatively small telescopes like the Hubble Space Telescope. Now, the fact that between dark energy and dark matter, that accounts for 96% of all the energy content in the universe, and we have no clue what either one is, gives us pause that, well, maybe we're not so smart yet, but plenty to learn. So just in terms of sensitivity, this is a plot that at the bottom shows the years and the competition for who can build the biggest telescope. And then sensitivity of improvement over the human eye. So our eyes are a unit of 1. Galileo's telescope was like 78. And then you go up through bigger and bigger telescopes with people looking through them. Around 1900, photography with these glass plates got us up to about 1 million times more sensitive than the human eye. And that's just by doing time exposures. Eventually, electronic detectors CCDs. And then the Hubble Space Telescope gave us a big jump because we got above the atmosphere, we had better detectors, and we could detect light that doesn't make it down to the ground. So suddenly we're into the billions of times more sensitive than the human eye, and capable of much better resolution because we don't have, the effects of the atmosphere scattering light. Stars twinkle here on Earth. I can tell you, looking out the window of the shuttle, they don't twinkle in space, other than intrinsic variations, but that's a different story. And then on this final servicing mission, we put in new cameras, the Wide Field Camera 3, and fixed the advanced camera for surveys that gave us another, leap to almost, hundreds of billions times more sensitive than the human eyeball. Now, you may remember that the Hubble was launched with spherical aberration, i.e. blurry images, and lots of jokes about the Hubble. This is a cartoon, one of many from the first photos from the Hubble, showing the moon looking like a peanut, Jupiter all distorted, Saturn with wavy rings, and lots of angry taxpayers. And I show this because for a few years, people were saying the same about James Webb. Maybe we should just cancel it. It's too expensive. It's too delayed. But fortunately, Congress has and NASA, we're determined. We're up almost to $10 billion, and it's now James Webb is doing great science. I don't know the exact statistic, but $10 billion is like 1 month of our support for Iraq and Afghanistan when we were still there in the world's, the US's longest war. It's a lot of money, but it's also a fraction of what, maybe 1/6 of what we've already spent on the SLS and Orion that will launch on Monday. So I think it's a bargain for what I think we will get. For Hubble, we launched in 1990. We fixed the spherical aberration in 1993. We put up the Space Telescope Imaging Spectrograph in 1997. And just as an aside, that's one of the instruments I'm using now to study Europa around Jupiter in the ultraviolet. In 1999, Hubble stopped doing science, and so we called up a special mission. This was my first mission to the Hubble, to put in new gyros, replace the 286 computer with a 386 computer, and a fine guidance sensor. In 2002, I went up and put in the advanced camera for surveys, solar arrays, replaced the cooling system on the near-infrared camera. We replaced the power system and a whole bunch of other things. And then finally in 2009, we went up and we repaired the advanced camera for surveys that had failed, the Space Telescope Imaging Spectrograph that had failed. We put in new batteries, gyros, Wide Field Camera 3, and finally pulled out the COSTAR instrument, which was the corrective optics for the spherical aberration, and put in the Cosmic Origin Spectrograph. And I'll just mention that virtually all of the instruments, all of the prime instruments, axial instruments, were built by Ball Aerospace in Boulder, and the principal investigator for the Cosmic Origin Spectrograph is Jim Green at CU Boulder. So a lot of Colorado in the Hubble. So that's me out in the payload bay with a big smile. You can see in my visor. Let's see, I'm not sure how to turn on a laser pointer, but you can see the Earth reflected in my visor. Above me is the wing of the space shuttle. You can see I have a big grin on my face. This is just a magical experience to be able to get into a cloth spacesuit and go out in the payload bay of the shuttle. And finally, I understood why everybody was asking me for most of my adult life, do I work in a vacuum? And yes, I do work in a vacuum. So here I am with Drew Feustel, my spacewalking partner, and we are installing the Wide Field Camera 3, which is a really amazing optical near-infrared camera. There's 2 detectors, separate channels, and this gave us our first glimpse of what the James Webb Space Telescope can do now, which is to have this near infrared channel and the visible light channel, and comparing the images. This is a video just to give you a sense of what it's like to do a spacewalk. This is from Drew's helmet camera and opening the doors on Hubble. And this is a shuttle camera on the end of the arm. And here we are pulling out the co-star, that's Drew, and putting that away. And then we'll switch to an image of me repairing the advanced camera for surveys, which involved cutting some metal grids and pulling out tiny screws. That's Drew on the arm, I'm inside the telescope. So here's my helmet camera coming up next. And you can see, how do you remove tiny screws in space? Well, with a tiny screwdriver, of course. But we didn't want the screws to float around. So I put on a special contraption and used a power tool to pull them out the rest of the way after I loosened them slightly. And then the screws were captured. Probably hard for you to see, but if you look closely, there's a clear window and you can see those screws floating around. And then I used another contraption, a card puller, to pull the circuit cards out for them that were failed. This is the first time we'd ever done board level repairs in space, in a spacewalk. The edges of the cards are super sharp, so they didn't want me handling them, because if I cut my glove, the oxygen would leak out and I'd die, and that'd be sad because we wouldn't fix the Hubble. So we finally finished our work. There's the Baja Peninsula going by at 5 miles a second. And coming into the airlock, I was pretty happy because the review teams, there's always a lot of review teams at NASA, said, we shouldn't even try this because it's too hard, it won't work, and we should be spending our time more wisely. And you can see by the smile on my face that not only did it work, but I had predicted it would take 2 hours and 30 minutes because I practiced so much, and it took 2 hours and 32 minutes. So we were very successful on that. And now we have an advanced camera for surveys on the Hubble, and all the rest of the repairs. And amazingly, so far we've lost 3 of the 6 gyros, which was predicted. And so Hubble is still doing great science. And now we have both Hubble and the James Webb Space Telescope to help us unravel the mysteries of the universe. Any good travelogue always has a sunset picture. This is actually a sunrise picture, but if you play it backwards, it's a sunset picture. And I show you this for a couple of reasons. One, it's just really pretty. And 2, I'm going to talk about doing spectroscopy of the atmospheres of planets around nearby stars through the transit spectroscopy method. And so this is the sunlight being transmitted through our Earth's atmosphere. And you can see the curvature there. That blue line is about 100 kilometers of atmosphere. And so when we have the James Webb Space Telescope, or Hubble, looking at another planet's atmosphere during a transit, and I'll explain that, we're looking at the sliver of light around the planet like this at 100 light years away. I think it's just phenomenal that we can do that with the Hubble and with the James Webb Space Telescope. So one thing that people don't think about is that our cell phones and the Hubble Space Telescope have monochrome cameras. So we take sequential images on the Hubble. So we'll take an image in red light through a filter, green light through a filter, blue light through a filter, and sometimes we'll take other colors. This happens to be H alpha, hydrogen light, particular line from hydrogen. And then we take those and we stack them on top of each other to create the beautiful pictures that we see from Hubble. And of course, your cell phone does that, but instead of taking them sequentially, there are filters over little sensors on your CMOS sensor in the camera, and it takes 3 pictures all at once, red, green, blue, and the computer puts them together and you see the picture. Let's see, there's, okay, I was just checking the chat. So that's how Hubble does it. James Webb is similar, but it also has other imaging modes that are different and important to talk about. So this is sort of a classic star forming region from the Hubble Space Telescope. You can see the resolution is really amazing. This inside of this pillar of gas and dust, taken in the light of oxygen, nitrogen, silicon, and hydrogen. Again, the colors superimposed. We can see the dense dust inside a new star is forming, and we know that because this is a Herbig-Haro object, and we can see the jets coming out. So we know inside there has to be something going on. And this is with the new wide field camera 3. And if we use the infrared channel and look at this same pillar, we can see through the gas and dust and see the star inside with those jets coming out. Now, the infrared light can get through the gas and dust just because the wavelength of the light sneaks through. It's a wavelength at about 1.5 microns to 2 microns, and the size of the dust is 1.5 microns to 2 microns. And so instead of the light getting scattered by the dust, it can sneak through the dust grains, and we can see not only the star forming in the middle, the young star that's only about 10 to 15 million years old, but we can also see through the nebula and the stars in the background. So I'll do that one more time. So what we see now is the gas and the dust being illuminated by ultraviolet light from nearby stars. So that's why this has this eerie green glow. And then in the infrared, we just see the stars inside and the background stars. Now, the other thing I want to mention is if you look at the bright stars in the foreground, those are the ones with the little crosses. Those crosses are the diffraction spikes off of the spider that holds the secondary mirror. So you can see that there's 2 spikes, and that's also what is holding up the secondary mirror on the Hubble Space Telescope is, basically a cross. You can also see that this image is diffraction limited, that the Hubble is achieving the best possible resolution because you can see the rings, they're called airy rings, around the stars. When we get to James Webb, it's going to look different. And I think you've probably seen the images. One of the things that Hubble has done is to set the previous distance record, looking back in a deep field. So this is the Hubble Ultra Deep Field. So this represents about a month of observing to get a really deep time exposure to see galaxies that are super dim and super far away. So this sort of blob that you see expanded is a galaxy that is only 400 million years old. So this is pretty well into that picture. The universe is roughly 13.8 billion years. For those who are interested, it's a redshift of 11.1. And this is at a time when, galaxies were still forming and hadn't, arranged themselves into beautiful spirals and such. So this is about as far back as Hubble can see. We just don't have enough time, and the light is redshifted. If you think about a wavelength of light and you pull on it, it gets redder because the wavelength gets longer. Well, the universe is expanding, so the wavelength of the light expands as it travels to us from these distant and ancient galaxies. And Hubble's red sensitivity just runs out. It's not an infrared telescope. That's why we built the James Webb Space Telescope. Now, this is a picture of the Great Nebula in Orion, one of my favorite winter observing targets. It doesn't look this nice in my little 5-inch Celestron, but this is what the Hubble sees. And one of the contributions to Hubble is not only the incredible science, but also that it's shown, astronomers and the world that the universe is really a very beautiful place. That it's not just points of light and smudgy galaxies, that it has really rich texture and depth. And with Hubble, we've actually been able to analyze the Orion Nebula and lots of other objects to get the 3D structure so that we can make simulated fly-throughs as if we were on the flight deck of the Starship Enterprise flying through at many times the speed of light. And this is one of my favorite images. Now, the James Webb Space Telescope was named after James Webb, obviously. It's not a spiderweb telescope, it's the James Webb Space Telescope. James Webb was the second NASA administrator. He's a former Office of Budget and Management, it wasn't called that back then, director. He was a U.S. Marine. He worked on radar, and a number of other things, so he's a very technical person. And in the Kennedy administration was named administrator, and he oversaw NASA during really the early part of the human spaceflight program up through 1968. And then politics, he was replaced before we landed on the moon, but just before the first Apollo launch. And what folks don't know about him is that he also was one who really pushed hard on a couple of interesting areas, one of which was science. He helped make sure that even though the human spaceflight program was getting a huge amount of money, that science would be a part of exploration, human exploration, and NASA's fabric going forward. He, basically convinced the president and the vice president that without the science component, NASA's program would have, a peak and a decline, and it would not be a long-lived agency, that the real meat was in producing great scientific results for reasons, similar to what I started with, that it would inspire the nation and drive people to go into science and engineering. As well, he felt like one of NASA's investments in the nation should be building space science centers around the country. And so the MIT Center for Space Research, the Cornell Planetary Science Lab, Georgia Tech, University of Chicago, WashU St. Louis, Caltech, many other laboratories around the country were started brick and mortar with NASA funding as the idea of James Webb to help stimulate science in the country. University of Arizona. He also felt like land-grant universities should have laboratories as well, and started a number, including, I think, at Iowa State University, I think he was from Iowa. So James Webb was, somebody who put science into NASA, and that was one of the reasons why Sean O'Keefe named the telescope after him. Now, generally, we don't name telescopes until after they're launched, but we've made a few exceptions, and James Webb was one of them. And astronomers were like, who's this guy? Why aren't we naming it after a famous astronomer, and so on and so forth. But I think it's well named. The other telescope that we broke the rules was the Parker Observatory, named after Gene Parker. And he was my electricity and magnetism professor at the University of Chicago. And I think that was also a good exception to name it while he was still alive, so that he could, be honored instead of memorialized. So this is the animation of the James Webb Space Telescope deploying, obviously at much higher speed. The telescope has a sunshade the size of a tennis court that blocks sunlight, and it had to be deployed first. And so you can see that deploying slowly. The sunshade has 5 layers of aluminized mylar and Kapton, and those 5 layers are separated, and each layer rejects some of the heat from the sunlight. It's like SPF 1,000,000. And also by having multiple layers, when micrometeorites go through a layer, it's unlikely that it creates a light path that makes it to the telescope. So after the sunshade is deployed, we deploy that's actually a drag, that little drag thing in the back is to counter solar pressure. Then the wings come out, then the secondary mirror comes out, and the telescope is deployed. Then we had to go and align all of the mirrors. So instead of 17 individual images, we had one image, just repointing them all to produce a single image, and then verifying that each one is diffraction limited by adjusting the center of curvature. Now, just to give you a feel, each of these mirrors is, a little over 1 meter across, and they're built out of beryllium, and they were ground at room temperature, but with a correction so that once they got down to 40 Kelvin or minus 390 degrees Fahrenheit, they would have the correct shape. As things cool, they shrink, and as a mirror surface cools, its surface changes. And we thought we might have to do a number of iterations of grinding the mirrors out of this beryllium, which is a good low temperature material, very toxic, cooling it, measuring it, warming it up, making another grinding correction, cooling it. But the team at Ball did such an amazing job that we really only had to do that once. And all the mirrors were ground better than the specification. It was really quite incredible. Now, to give you a sense of how smooth these mirrors are, I did the calculation that if you were to expand one of these mirrors to the size of the United States, the average mountains would be 2 inches tall. So it's incredibly smooth. And that's one of the characteristics that's allowed it actually to exceed its specifications once we finally got on orbit. We have 4 instruments. We have a near-infrared camera, basically, a series of detectors in the focal plane that make images, and filter wheels like Hubble that can give us several different infrared colors. We have a near-infrared spectrograph that takes a portion of an image and breaks it into its component colors to create a spectrum. Then we have a mid-infrared imager, and I'll show you, I think I put in some wavelengths. So going from a few microns to 5 microns, and then from 5 microns to 10 microns. And then the fine guidance sensor also has an imager and a grating so that we can do near-infrared images and slitless spectrograph. So each image is split into its colors in the image plane rather than taking the light individually and making a spectrum. And so the combination of all these instruments allow us to do the science. So the science that we intended to do is to try and understand that very early universe, the first light, the first stars, galaxies, and how the universe emerged from these dark ages. Were black holes, early on, creating a lot of X-ray light? Was it these massive stars that only lived for tens of millions of years, going supernova explosions? What was the story of the birth of matter and stars, galaxies, and the universe? How did galaxies assemble through cosmic time? How did we get, these nice spiral galaxies? What's the story of the birth of stars and planets? Looking into those dense regions of gas and dust that optical telescopes, visible light telescopes, can't get through, the infrared light gets through, so we can study, the origins of protoplanetary disks and the formation of planets and stars. And then more recently, it was just, it's only 1995, well into the development of the telescope, that we realized that basically every star has planets around it. Really, Kepler is what told us that. So James Webb sort of accidentally is perfectly suited to look at exoplanets, exoplanet atmospheres, and hopefully get us closer to that question of, are we alone in the universe? James Webb is probably too small. I know there's a lot of hyperbole out there, but unless we're really lucky and there's a star with planets around it very close, that we'll be able to detect signs of life in a planetary atmosphere. A planet like Earth is just too dim, really, to be able to see with the James Webb Space Telescope, but we might get lucky. So what would we be looking for with the James Webb if we're studying a planet's atmosphere, a rocky planet like Earth, if we're so lucky to find one really close? Well, this is an image actually from the Cassini spacecraft looking back into the plane of our solar system. That's what that line is. And that little blue dot in the middle is Earth. And so that's the dicule dust that we're seeing. That's basically, junk left over from the formation of the solar system that just keeps orbiting the sun and coming in from the outer regions. And if we were to analyze the light with a telescope like Hubble and James Webb, then we could break that light into its component colors. And for the Earth's atmosphere, we would be able to see carbon dioxide, methane in the near infrared, water vapor in the visible and very near infrared. And so each of these little dips, this is the intensity of light up and down, the wavelength right and left. And so these characteristic dips are the signatures of molecules like water, carbon dioxide, methane, in some cases atoms, oxygen and ozone, ionized oxygen and ozone in the atmosphere. And each of these little wiggles is characteristic of the composition of an atmosphere. And then on Earth anyway, plants tend to absorb light at a characteristic frequency that we can see in the general shape of the spectrum. So the James Webb Space Telescope territory is in this, red, near infrared, mid infrared portion of the spectrum. And so we should expect, looking at planetary atmospheres, that we will be able to see water vapor, carbon dioxide, and some other things that are critical perhaps for detecting signs of life on another planet, or at least habitability. Could a planet be habitable with those components? So fortunately, James Webb left planet Earth on Christmas. I think it was a marvelous Christmas present for everybody on planet Earth. That's the Ariane 5 rocket. The European Space Agency not only contributed an instrument, the mid-infrared instrument, but also the rocket that gave us a ride to orbit. And what a ride it was. Not only did it get us on our way from Earth to a point 1 million miles away from Earth, but it did it so precisely that it gave the gift on Christmas 2021 of not having the James Webb Space Telescope have to use propellant to get to its final orbit. We built the James Webb Space Telescope with a 5-year requirement for propellant, and that's its lifetime nominally. But we knew that we'd be able to put enough fuel in that if we got a good ride to space, that we might get 11 years. Now, we use propellant to station keep and also to take momentum out of the gyros if they saturate, that we use to point from place to place. But the injection into our orbit was so perfect that we believe we have 20 years of fuel on board now. So off we went, and the prediction for how long it would take to deploy the telescope on its way out to Earth Sun L2, this point beyond the Earth and Moon, so that we have the Sun, the Earth, and James Webb 1 million miles away. We predicted it would take 14 days, 2 hours, 40 minutes, and 33 seconds to fully deploy. And it ended up taking 14 hours, 14 days, 3 hours, 8 minutes, and 31 seconds. And that's because there was one little snafu that we delayed a deployment slightly just to make sure we understood what was going on. So really remarkable that all of this was planned so precisely and has gone so well. There were hundreds of deployments, any one of which could have made the telescope absolutely useless. And I'm still amazed to this day, even though we're now 9 months into this, that it all deployed perfectly without substantial troubleshooting. And while Hubble was designed to have extreme servicing, almost everything could be fixed, James Webb was designed with 0. It had to work exactly as designed or it'd be a complete failure. And there's no way, no matter how much we would want to send me to space or somebody, some astronaut to go fix it. It's just not possible. So out it went, and we aligned the mirrors to make one image pointing at a very bright nearby star. And this is that image, the final image. And so what you can see is, unlike Hubble, which has a symmetry due to the cross where the mirror is held, James Webb has the hexagonal segments with gaps between each one, and then 3 supports for the secondary mirror. All of that combines to make an image of a bright star that has these this other star-like pattern, and that's the diffraction. And if you suppress the light from the middle star and look very close, you'll be able to see that we've achieved diffraction limited imaging at 1 micron, which is better than the specification, which was diffraction limited at 2 microns. But what's really beautiful about this picture is that in the background, the picture was just this bright star so that we could align all the mirrors. And in the background, you see a sea of galaxies. 30, 40 years ago, there'd be, half a dozen PhD students working on that background image to get their PhDs. And here we're doing an engineering image, and the sky is filled with galaxies. And so just in that 30-minute exposure of that bright star, we have a new catalog of galaxies in the infrared. Really, really quite phenomenal. It's like the excitement from the deep field on Hubble when Bob Williams proposed it, and for 10 days we observed, a blank section of sky, and out came all these galaxies. Well, in 30 minutes, we have a deep field. So this is a picture with that wide field camera 3 that we installed on Hubble in 2009. It's, obviously with a number of different filters, and it shows, the incredible resolution of Hubble in visible light and ultraviolet light. And with Hubble, we've been able to, watch weather on Jupiter, watch the evolution of the Great Red Spot, obviously all the moons of Jupiter. We even detected, rings around Jupiter and aurora and other things. And so now I'm going to show you just because it's fun, the James Webb Space Telescope image of Jupiter, and it's equally exciting. And in fact, you can see, some evidence of auroral phenomena, atmospheric effects, dust scattering in Jupiter's atmosphere. And, these are false colors. Again, multiple images with NIRCam stacked on top of each other. And what I find interesting and exciting, one of the things, is that because James Webb is looking at longer wavelengths of light, and because it's achieved diffraction limited performance at 1 micron, if you compute the resolution, the finest detail that James Webb can see, which is basically the wavelength over the diameter of the telescope, and the same for Hubble and the ultraviolet, we have 2 telescopes that cover from the ultraviolet, at a few hundred nanometers, to the infrared with light that's up to 10 microns at about the same resolution. And so we can go back and forth and compare details of the same size on an object like Jupiter. And I'm really excited because sometime in December, I believe, we're going to observe Europa. And with Hubble, myself and collaborators have seen evidence of plumes of water coming out of Europa. And we're waiting for James Webb to verify that, where it can actually spectroscopically analyze it. And if that's true, then like Enceladus around Saturn, we could fly a spacecraft through and see if there's any signs of life in the ocean on Europa. This is the Carina Nebula taken by Hubble. Again, this is a star-forming region. You can see that the gas is being evaporated by bright ultraviolet light from nearby stars. And in those dark regions, stars are forming. In particular, you can see here's a brand new star that's blowing a bubble around itself. And we know from zooming in on these images that when the stars are formed, a protoplanetary disk forms about the same time. This is, like the Eagle Nebula pillars of creation. But we can't see into the nebula, and we can't see through the gas and dust that's being blown off of this nebula very well. The background stars are attenuated. So I made this PowerPoint presentation this afternoon, so it's not perfect, but here's the James Webb. This is a larger view, and you can tell it's James Webb because, again, you look at the stars and it has all these different points because of the hexagonal symmetry. But just, we're seeing into the nebula. And I'm going to superimpose the Hubble image for a moment after hopefully the bandwidth is sufficient that this is filled in completely. And all of these are online. I'll give the websites later, and I just encourage you to explore these images. So there's the Hubble image, and the James Webb image is higher resolution, but that's because this is a wide field planetary camera 2 image from Hubble, and not the new wide field camera 3. It would be 4 times the resolution if we were using the new camera. So I'm going to go back. And then not only that, but the James Webb has both the near infrared channels. This is the near cam image, but also the mid infrared image. So here's that mid infrared image superimposed. And now we can see even deeper and different details into the image. And so this is just going to be an amazing new tool. These are still just engineering images from which we're already getting great science. This is an image of, well, this is an artist's conception of a nearby exoplanet. I don't know if I can move this on my end. WASP 39b, let me try and get that out of the way. And it's a planet that was observed from a wide field planetary survey, ground-based telescopes. It's around a star that's smaller than our sun. WASP 39b has about the mass of Saturn, but it's larger, just a little 30% larger than Jupiter. So it's not very dense. It's kind of a puffed up star because it's so close to the sun. It's about, Jupiter is relatively cold. This is about 900 degrees C. And so the star is puffing up this and heating the star. So it's got this low density. And so let me talk about transits a little bit, because I'm going to show you the early results from the James Webb Space Telescope on transit spectroscopy, which will allow us, as I mentioned, to analyze the atmosphere of this star. So if you look at a star flat on with a planet around it, you can't really tell that the planet's there. But if we're looking in the plane of the orbit, when the planet goes in front of the star, the light dips down a tiny bit because the star has blocked out that light. Now the star is illuminating the planet. So when the planet goes behind the star, a tiny bit of light is also taken away. And so if we study the light curve of a star and we see dips, it might be due to a sunspot, but it might be due to a planet. And if we study it carefully enough, we can tell the difference and measure the period of orbit of those planets. Now, the other thing that we can do, so Hubble has studied WASP 39b, as has Spitzer, and we've been able to break the light up from the transmitted light through the star's atmosphere into its component colors. That's the wavelength along the bottom, and looked at the relative intensity. And we've been able to identify with some modeling hydrogen and helium, that's not a surprise, sodium, potassium, and water vapor in the atmosphere of WASP 39b. But as we get beyond 1.5 microns or so, Hubble runs out of sensitivity. It just can't observe anymore. So we use the Spitzer Space Telescope, an infrared telescope, but it only has 2 colors, around 3.5 microns and 4.5 microns. two band passes and filters. And so we made two little measurements. But if you look at the proposed spectrum model, which is the blue line, you can't really tell very much. There might be CO2 in the atmosphere, but it's not conclusive. So with the James Webb Space Telescope, we've been able to observe WASP 39b. We've been able to see that transit. So this is the starlight when the planet is away from the star. When the planet goes between us and the star, some of the light is blocked. And while it's in front of the star, some of the light is transmitted through the atmosphere. And then the planet goes back outside of the disk of the star and it goes back to starlight. So if we study the bit that's at the bottom here, we can see that there's, in different colors, different amount of light is absorbed. Well, that's the spectroscopy component. So some of the light is absorbed, and if we actually use the spectrometer, the near-infrared spectrometer on the James Webb Space Telescope, we get the amount of light that's blocked, which are these little dots, percentage. So for instance, this is 2.17% of the light is blocked at 3 microns in this one color. And we go along, we end up seeing that in fact there's this bump. And this bump, CO2, at 4.45 microns corresponds to carbon dioxide. That's the color of light that carbon dioxide absorbs. So we've definitively identified carbon dioxide in the atmosphere of WASP 39b, hundreds of light years from Earth. So that's pretty cool. This is a Hubble image of 5 galaxies, 3 spiral galaxies, and 1 kind of elliptical galaxy. They're at different distances. These 2 that are about the same color are close to the same distance. This guy is closer, and this elliptical galaxy is further away. All of these stars, again, you've now learned how to identify that it's a Hubble image because it has the cross, are foreground stars, and we're looking much farther away. And you can tell that there's, galaxies all over in the background that are even further away than that. And this is just a beautiful picture where the galaxies happen to be very close together. These 2 are actually close enough they could be interacting. And in fact, this galaxy has been disturbed, the one in the middle, by a collision with another galaxy. And in the shock waves that collision has created, we can see all kinds of stellar birth activity going on in a stellar nursery. So we call that a star burst galaxy or starburst activity. You can see a lot of new stars being born here, all these red areas, and that's because we've zoomed in on a particular wavelength of light with a filter that identifies, hydrogen burning stars. So that's in the visible and near infrared. And now we go to the James Webb image, and because it's infrared, we've been able to see through some of the gas and dust. Again, a lot of what we can't see here is blocked by gas and dust in the galaxy. We go to the infrared, and now we can peer much more deeply into the middle of the galaxy, and we can see those star-forming regions in the infrared, much more visibly. In Hubble's case, we're using ultraviolet light. Those hot stars are producing lots of ultraviolet light. And here we can see it because it's the gas and dust that's collapsing and forming those regions. But also take a look in the background. In Hubble, there are quite a few galaxies that come through, but because the James Webb is infrared, it can see those galaxies that are further away, and it's got more light gathering power because of its size. We just see a lot more stuff in the background. So again, just incredibly cool. Now, I think you probably all know that basically at the center of every galaxy is a massive black hole. And so with this near spec imager and the mid-infrared imager, combined, we can do spectroscopy and imaging of parts of the galaxies. So if we zoom in on this particular spiral galaxy, and this one is one that's undergone a recent collision because we can see that it's been tidally disrupted. There's a tail of gas and dust coming out with new stars forming. But in the middle is a putative massive black hole, millions of times more massive than our sun. And we can do spectroscopy of the region right in the middle and of the gas around it. And so if we look at the gas that's around it, which is presumably, a lot of stars, we see a typical stellar spectrum. We see, iron, argon. So iron created in the core of stars in the stellar furnace, fusing all the way up to iron. We see argon, neon, sulfur, a bunch of neon lines, more sulfur, oxygen, and neon. And then for some reason, when we look right in the region around the central black hole, we see a lot of hydrogen. Well, that's because gravity is pulling that H2 molecular hydrogen into probably a big disk circling around the black hole. More molecular hydrogen, a bunch of other lines that are neon lines and stellar lines, and silicates. So, these are presumably, dust grains that are accumulating in that disk from stars going supernova and putting, all kinds of dust and gas back into the interstellar medium around that black hole. So this is the kind of science that we're able to do with James Webb that we couldn't do with the Hubble Space Telescope. We're all familiar with, Hubble deep fields and Hubble gravitational lenses. Again, if I were to do a quiz, you would all guess correctly. This is a Hubble image. There's all of these really bright galaxies are forming a galaxy cluster. If you look up in the universe, galaxies tend to cluster into groups and little filaments in the universe because of dark matter. And all of the galaxy matter, normal matter like us, and the dark matter creates a gravitational lens. So light gets bent around it. And so we can see like this galaxy, the image, this galaxy is much further away than the cluster of galaxies that's creating the lens. The image is magnified and distorted. This image would be tiny if it weren't for this collection of mass that's causing the light to bend around it. And some of the light is stretched into these arcs. And if you could recreate some of the arcs that are at the same distance, you would find out that it, and do the reverse imaging, they would create, a picture of a galaxy, but they get distorted by this gravitational lens. And you can kind of see the general symmetry of light from distant galaxies getting bent around. So this is with the Hubble Space Telescope. And then here's the James Webb Space Telescope image of a similar, not the same one, but a similar galaxy cluster. And again, we can see, distorted images, and it's not the angry taxpayer distorted images. These are actually gravity doing its work. And we can see, all of these galaxies in the background. Now the stars are in the foreground, so they're not affected. And it's just a cornucopia of galaxies and distant galaxies. And the more red they are, the more far away they are. And so again, we can do spectroscopy of individual galaxies and even these warped images. And that can tell us how far away the galaxies are. So as the universe expands, remember I told you that light from very, very distant galaxies is stretched out. It's more reddened than light from close galaxies. They're not stretched out as much because they're closer. So we can take individual galaxies, basically every speck of light that you see, other than the ones with the crosses. But if I pick out some tiny little speck, like that speck, that's actually a whole galaxy with billions of stars. So you can zoom in, so to speak, and take just the light from one of those specks and then analyze the colors of light in a spectrum. And you can find out that the light from hydrogen and oxygen, for instance, find those spectral lines where the hydrogen is emitting, the oxygen is emitting, and it's way, way out here at almost 5 microns. that then translates into an age of 13.1 billion years. Now, I showed you a galaxy from Hubble that was 13.1. It was the image as it was 13.1 billion years ago. Here's one that's not quite as old, 13 billion years. This one is, these are almost baby galaxies. This one's a toddler galaxy at 12.6. And here's the light from its galaxy. So you can see it's not redshifted as much. And here's one much closer, but still quite far away, actually, 11.3 billion light years time distant. And here's its. But what's really amazing is how much quicker the Webb telescope is. We spent, weeks getting the ultra deep field image with Hubble. It stared in one region, for 11 days to get a deep field. This image was 12 hours.
I could put this on mute. Don't stay out here.
So here's that 13.1 billion year galaxy. And if we look at it in more detail with the near cam, this is the image, and the near infrared spectrometer, we can get a very detailed spectrum to try and figure out how old are the stars in this galaxy. Are they all brand new stars, or have they already evolved by the time we got, to 600 million years old? Have they already evolved into stars that are creating a lot of heavy elements? And so what we're seeing oxygen and neon. And so in the stellar nucleosynthesis, we start out with hydrogen and helium, and we burn that into carbon, nitrogen, and oxygen. And then as the star goes into its next phase, it starts burning to neon, magnesium, and the heavier elements, silicon. So we're starting to see neon. So actually the stars in this galaxy are already pretty far evolved by the time the universe got to 600 million years old. But this is just with a 12-hour exposure. Once we do a really deep exposure with James Webb, hopefully we can start getting back to the stars that are 400 million years old or 300 million years old. This is just a pretty picture of the Pinwheel galaxy, again, highlighting, the difference that we can see between, Hubble images and the James Webb Space Telescope, where now we're able to zoom in on structures like these spokes that we weren't able to see with the Hubble because there was too much gas and dust in those galaxies. So that's kind of my quick review of where we are with James Webb. So far, everything's working on the James Webb just as planned. It's producing amazing science every day. Something new comes out. That Jupiter image is only a few days old. Okay. And if you go to webbtelescope.org, you can find all of the images that I showed and more. There's also a blog where engineers and scientists write about what's going on, blogs.nasa.gov/web. And of course, all the Hubble stuff is on hubblesite.org. And so I think I'll stop there, and folks we can have a discussion.
Okay. Oh, wait a minute.
Aliens are invading.
Yeah.
Okay, if everybody's got that, I can stop the share.
Okay, well, I tell you, that was unbelievable. Never mind Hubble hugging, but universe hugging is really your call to duty. That was great.
Yeah.
The only question I can think of right off the bat, I remember you telling me that you wanted to have something on the JWST just in case things didn't unfurl, and you could shake it through a robotic arm or something. And so at the end of the day, you said something that just bothered me a lot. Can we, we're getting to where we are going to be out in that range can we do anything with Jim Webb to fix things or pull out stuff, or is it just packed up and sealed so we can't do that?
So a few things. So the discussion that we had, gosh,
Yeah,
10, 12 years ago,
yeah,
it was about 10 years ago that we had this discussion, is that I wanted to put a small grapple fixture. Really, I showed about this big.
yeah.
That's how big it was. It was made out of titanium. It's built by the same folks that built the Canada arm. And they had a spare one that weighed 0.44 kilograms and was perfect to put on James Webb, in that a grapple fixture has a base and a pin,
Yeah.
and the pin was on springs, so that if you grabbed it, it wouldn't put any moment into the telescope. And I wanted to put it on the bottom of the spacecraft so that if something didn't deploy right, we could send just a little spacecraft up, not much bigger than a CubeSat, that would have a motor in it that could shake the telescope at the right frequency while we commanded, whatever it was that was stuck to drive, in case it was just stiction, right? A little more friction than we expected. But fortunately, that wasn't needed. But the other thing I wanted to put on the telescope were targets, because if you're coming in for a rendezvous, not people, but a robotic spacecraft, but if people were there, same thing, and you look in your zoom lens to try and find where you are on the telescope, on the spacecraft, you can't accurately, and certainly robotically with a vision system, you can't accurately find that grapple fixture and grab it unless you have some fiducial markers, which are targets. And so when I directed the program manager, Bill Oakes, project manager, Bill Oakes, to put this grapple fixture on, he refused to do it. And he refused to do it because he said, well, today, John, you want a grapple fixture. Tomorrow, you're going to want me to make observatory fuelable. And then you're going to want to be able to change out instruments, and it will never end. And I said, no, all I want is the grapple fixture and the targets. So we finally settled on just putting the targets on, so that some future generation could, in principle, come up with a way to grab the telescope. I think we lost our opportunity without the grapple fixture, but in principle, it could be done. But you need those fiducials. So there are stickers on the telescope that, an alien spacecraft could maneuver and find where it is.
Yeah. Great. Okay, thank you.
But the reason why we put those stickers on there was in case somebody could figure out a way to refuel it. And we did some experiments on the International Space Station called the robotic refueling mission. And we showed that with the valves on James Webb, you could robotically take the caps off, open the valves, and refuel the telescope. Everything unfurled correctly, so we didn't need to shake it. And the launch was so perfect that we have 20 years of fuel, such that after 20 years, the detector sensitivity will have degraded, and probably a few things will have failed by then, such that I don't think we'll have to refuel it either. Now, the other side of it is, you said, well, we're going to be going out that way. A million miles from Earth is, 4 times further than the moon. We're not really planning to go out that way anytime soon, although the Roman Space Telescope will be out there. And it has some limited serviceability, like refueling. But the James Webb is so delicate that if you tried to get close to it, say with an Orion capsule, just the little puffs of gas from the thrusters would fold up those solar arrays, like they were, some kind of thin paper.
Okay. Thanks, John. Any more questions from everybody online?
Sorry. Yeah, I think I unmuted or you can unmute yourself now.
And you can raise your hand too.
And yeah, if you can raise your hand, that'd be great.
Under reactions. So you can,
Yeah.
like that.
Oh, that's advanced. Advanced strokes.
Well, they're applauding. You're
Oh,
top.
thank you, thank you.
Yeah, really, yeah.
I have a quick question. Could you, John, please talk briefly about micrometeoroid impacts and any issues regarding them with regard to that really large 6.5 meter diameter mirror?
Sure. So I mentioned that one of the reasons why we have 5 layers of sunshade is that if you have one layer and a micrometeorite goes through, you have a hole. And, as the telescope orbits the sun, it's entirely possible and likely that the sun will be at an angle where it goes through that hole and hits the telescope and blinds the telescope. So we have 5 layers because it's pretty unlikely that you'll get the right angle through all 5. And we knew ahead of time that we would get hit periodically. Well, I was surprised, and I think pretty much everybody was surprised, that actually we got hit on a mirror, in the first few months of operation. And we can see that ding in the mirror for light that's coming from that individual mirror. We can see that there's, a little bit of distortion. Now, it's not enough to ruin the telescope by any means, but, we were sort of thinking that, once every few years we'd get hit by something and, damn the luck if we didn't get hit right away, such that people are sort of saying, well, maybe we don't know what the density of micrometeorites is out there as well as we thought. I mean, we've flown plenty of spacecraft through that region. We've had other spacecraft at Earth Sun L1, other telescopes, but nothing that big. That's sort of a big dust collector, if you will, and completely unprotected, right? I mean, if you have a telescope out there that has a shell like Hubble, the outside of Hubble is peppered with shots and holes. The high gain antenna has a hole the size of a quarter from something going through it. But we know that near Earth orbit is really dirty because we've made it that way, and other junk. So there is some concern that we're going to get hit a lot more than we expected, and that eventually it may start degrading the performance. But the mirrors are not glass; they're not going to break. They're beryllium. So when something comes in at 11 kilometers per second, the size of an amoeba, it just makes a tiny crater. It doesn't really do anything more than that. It does disturb the optics slightly.
Thank you.
So that's something we'll keep an eye on. Maybe if we have a meeting, hopefully in person in a post-COVID world, 5 years from now, you can ask me again and say, hey, John, how many hits have we had?
Thanks.
Yeah, good question.
Well, I have a question. Being a sometime amateur astrophotographer, I know all about guiding problems to get a good image. Does the Webb telescope, does it seem to be getting about as much solar wind blowing it around and solar radiation when it's imaging, or is there more or less, or is there been any feedback on that?
So it's been pretty much as we've expected. You may have seen after the sunshade deployed, there was a little tab that came down, and that's actually, a trim tab that was added late because it was realized that just the distribution of solar pressure on the star shade would cause an imbalance, and they added a trim tab to rebalance it so that we wouldn't have to use more propellant to desaturate the reaction wheels, which are what hold it steady. But right now the pointing performance has been exceptional. It's measured in the milli-arc seconds of pointing jitter from disturbances.
So it's well within the capability of what's going on in the environment.
Yep.
Nice.
And of course, we're moving towards solar maximum. So, the solar wind is just going to increase. But we'll,
Thank
it's
you,
11,
thank you.
it's a 22-year cycle, so it'll get better in a few years again.
Thank you.
How is it decided what photos a Webb telescope will take?
So
What goes into that decision?
So in the lead up to the launch of the telescope, there's the early release science that was decided by, a whole group of people to be both great science, but also good engineering to understand how the telescope is working. And there were just large community meetings and things where that was all kind of put together. And then there's the first cycle of observations. And again, that was decided before launch based on proposals. So pretty much anybody in the world could propose. And usually people propose in large groups, you get together people working on the same problems. And so you're all collaborators. And then they strip off the names and the institutions and any identifying information from the proposals, and they go through a blind peer review. So they're reviewed by folks who are not proposing and who are experts in those fields and rated. And then the top rated then they look at how much time is available, and the Hubble can look almost anywhere, anytime, not towards the sun. And James Webb is a little more limited because it has that sunshade. So they do the puzzle pieces to figure out, when James Webb Space Telescope can look in certain regions over the course of a year, and they populate the top proposals until there's no more time, and then they cut it off, and those folks get observations. And so that the next, I think, year and a half is already scheduled in principle.
Wow.
For all the observations. And sometime later this year, they'll release the call for proposals for the next series, and they'll select proposals. And if you didn't win the first time, you can improve it based on the comments and put it in again.
Thank you.
So the simple answer is peer review. The highest priority science.
Yeah.
And that's how Hubble works too.
I liked the explanation. That was helpful.
Yeah, John, John Grunsfeld, I wanted you to know a little more about who is on here. We have a number of, John Azatolis just asked you a question. We have a number of astrophotographers and people who know a lot about astronomy. And then we have, a number of us, I'll include myself there, is more general public. And that was just a wonderful talk you gave us. We really appreciate that. We also invited about 7 different Colorado astronomical societies. So we have some of those people on as well. We've got about 40 people, which is the most we've ever had. And I just wanted them to have an opportunity to ask questions as well. Also, well, I'll say more later. John Williams, I'm so sorry. He was our host. He turned it over to me. I'm not as experienced as him, and he's given us talks on the Hubble over the years too, but I'm so sorry he can't be here right now.
We're taping this.
And we are recording it, but he's actually they're selling their house and leaving Monday. So that's partly why he started this out, the host, and then turned it over to me. So I haven't wrecked it yet, glad to say. I think I unmuted or made it possible for everyone to unmute themselves. So if there are other questions, please go ahead.
So I have a question. John Grunsfeld has a question. At 36 and Nelson Road, on that corner, the southeast corner, there's a super modern house. It's relatively new. It's about 2.5 years old. And he or she has an outbuilding that's a neat little observatory. Does anybody here know who that is?
Oh, that's in Boulder, right?
It's in Boulder, yeah,
A 30
Boulder County.
David Elmore, do you know? That sounds like it's in your area.
I do not.
Have you
Yeah.
seen it?
Is it new?
It's about two and a half years old.
Okay.
It's just, somebody spent a lot of money and they've got a small
Dome?
building and a dome
Ah,
and
Yeah.
cars going by with headlights. It's near
Oh, no.
it's not that far from the NOAA antenna site.
Yeah.
It's right up against the foothills. I mean, it's reasonably dark, but
Yeah.
We'll
anyway.
look into that.
Yeah, we'll find out.
Okay, and then so I have another question.
Yeah.
When I first came here, I was trying to be very low profile. And I spent about 6 or 8 months fixing up the house that we bought before my wife came out. In 2016 in Washington, D.C., while I was a senior executive in the federal government, there was an election. And elections have consequences. And I decided to leave federal service. And that's all I'm going to say about that. But so in early 2017, when I just come to Boulder, I was in a Home Depot. And I was wearing grubby clothes and unrecognizable. And somebody came up to me and said, "Are you John Grunsfeld?" And it was, a really nice fellow. And he sent me a note, and I don't have it anymore. But he said he and his fellow neighbors operate a 0.6 meter telescope up by Nederland. Does anybody know anything about that?
Carolyn, I bet, yeah, she's raising her hand.
Yeah,
That area.
I think I might know who it is, but I have to ask somebody else. Because somebody referred him to me for a reason and I never got a chance to get hold of him. So I'll have to go back through my old email.
Okay. Anyway, I thought that was pretty cool. That's a big telescope.
Yeah.
Yeah.
Actually, I have a question for you, John. When JWST was looking at Jupiter, how difficult was it to track?
Oh, great question. So one of the things that we built into the software for James Webb, as we did on the Hubble, was the ability to track fast objects. And Jupiter is fast, but James Webb can track Jupiter just fine. It can track Europa around Jupiter, which is important to me, and many others. But it can also track comets and asteroids, other things, flying through the solar system. So it's one of those capabilities that is really exciting that James Webb can do that. Now there are limits, but so far it looks like the attitude control system and the tracking, is right on. So Jupiter was not particularly hard. The real challenge with Jupiter is it's so bright and the telescope is so big. You have to be careful and make sure you have filters that are cutting the light down because the telescope's so big.
Yeah, I wondered about comets. That was my original area of study under Jack Grant when I was in grad school. And I remember hearing about some of the early they wanted to build into JWST and then wasn't sure about comets. So, and we just bought a new so we're hoping to look at comets with it at some point.
But Carolyn, could you repeat that?
Sorry, I said we just bought an EV scope too, and we're hoping to look at comets with it. But I remember early in the process of planning JWST, the question was the tracking, and comets were mentioned, but it was more about planets at the time.
I bought a Meade tripod with a tracking system, and my requirement was it had to be able to move fast enough to image the ISS. Something
Oh.
I've not tried yet. And I bought it a decade ago.
Way fast.
Yeah.
No, I don't even keep track of it.
Yeah. Hey, John, one thing that I remember you telling me, and I think we need to salute you on this one. The Mars helicopter on a Perseverance mission just got off the ground again. And, you know, it probably wouldn't be there unless you, in your NASA role, didn't kind of help defend that engineering test vehicle that's turned out to be a real plus for NASA.
I can guarantee it wouldn't have been on if I hadn't have really pushed that as a NASA Mars hack, because you know the folks that proposed it to me were great, and JPL management was mostly on board, but outside of that, everybody thought it was a terrible idea. You know, it would be expensive, it would be risky, and it would, you know, potentially damage the rover, and programmatically they really needed just to focus on job one. And I thought it was both interesting, important, and NASA should be doing things that are risky and hard, like flying a helicopter in a Mars atmosphere. You know, I mean, the first A in NASA is aeronautics. You know, and who says we can only fly aircraft on Earth, right? I mean, what about Venus? You know, what about Titan? Well, because of ingenuity, and in part, we now have an octocopter going to Titan to fly in Titan's atmosphere. So,
and also now we're embracing it for the Mars sample return mission.
Yeah. Which is really funny, because the reason why they're embracing it is because 2 helicopters is a lot cheaper, you know, than a fetch rover. And I used to joke that we should put a hook on Ingenuity so that it could pick up the samples. So, but yeah, you know, management all the way up to the administrator, at every opportunity, they tried to kill that.
Yeah.
Thank
Yeah.
you.
Thanks.
Yeah, I want to give the opportunity of other people to ask questions, but if no one has one right now, John, I'd be curious what you think about going into Valles Marineris, like either on the edge with a mission, you know, and down
On
into
Mars.
On Mars. Yeah, for those who don't.
You know, I think it'd be cool. There's some speculative suggestion that there's still geological activity in the bottom of Valles Marineris, you know, some fault lines that could be relatively recent. And, you know, it would be spectacular to fly through that canyon. I mean, it's so much bigger than the Grand Canyon. The Grand Canyon's, you know, people occasionally fly through on scenic flights, and it's spectacular. You know, the question is, you know, from a NASA, you know, science hat perspective, is what science could we get by, you know, by flying through? You know, the helicopters are wonderful, but it's quite challenging to fly on Mars. And so the flights are very short. So I don't think we want to fly, you know, in the next, you know, probably 20 or 30 years, a helicopter through Valles Marineris, but we could fly a glider, you know, a powered glider quite effectively if we could get one to Mars and fly through with something less solar powered, basically a motor glider, if you're familiar with that term. So it's a glider, but it's aided by a very small propeller to counteract the little bit of drag that gliders have. It would be quite phenomenal.
Yeah. Anyone else with questions? And
Well, I could ask another one.
yeah.
How would one power a helicopter around Titan?
The Dragonfly mission has a nuclear power source.
Oh, okay. Yeah,
So
I was wondering.
it's a small mass of plutonium surrounded by thermocouples, basically. And so you create electricity that way. So it has a battery. You sit on the ground, you charge up the battery. When you have enough juice in the battery, you take off, fly around for a while, you go land, do a bunch of science while you're charging up the batteries again.
Okay. Very nice.
It's a, you know, it's a nuclear powered drone.
Yeah, thanks.
Yeah, it's, you know, you're so far out, there's no usable sunlight for something like that.
John, you know, the thing I'll be a reporter kind of guy.
It's the kind of guy you are.
Yeah. How about the biggest disappointment you've had in your career there? You know, working with NASA, astronaut, you know, and what your experience base, you clearly have had some successes, but what thing drives you crazy that you couldn't get through the system?
So there's professional disappointment and personal disappointment. I can't say that I'm really disappointed in the personal one, really, but I'm still a human being as much as, I claim, what are we, that I'm Spock. But I worked very hard on the International Space Station. I helped develop most of the spacewalking techniques and did a lot of the engineering runs in the underwater pool for how to assemble the space station. I led the team that developed all the software that runs on the laptop computers to control the space station, the inventory management system and barcoding scheme, although people complain about it, I initiated that. The IT architecture with the networks on board, I pushed through. I had program managers who said, well, astronauts don't need a network on the station. And so I developed a wireless network that we added on later. And then eventually we put wires outside because the program manager said, you don't need a network. So we had to wire it outside. But anyway, a lot of that stuff. And then I went to Russia and trained as a commander for the space station. When Mike Griffin, pulled me back to go to Hubble, I was hoping that maybe after the 2009 Hubble mission, I'd have a chance to go up and live on the space station for 6 months or maybe a year. And management told me that I was too experienced to go back to space, that they wanted to give, some of the younger people a chance. And so I left and I went to Space Telescope Science Institute as deputy director, which was a great job. And about 3 years later, there was a inspector general report that said that, NASA kept telling people who had experience to leave, like me, and that they didn't have enough experience to do the space station. And so the few people who remained got to go up to space station, who were, not all necessarily the most qualified. So that was kind of disappointing personally. Professionally, I'm disappointed that, myself and John Young, the Apollo 16 astronaut, and many others were unable to get NASA to come up with a reasonable architecture for returning to the moon and going on to Mars. On Monday, hopefully, we'll successfully launch the Space Launch System with the Orion capsule. And the people who built that are all great people, but it's just a horribly designed system. The capsule is so big and so heavy that we had to build the world's biggest heavy lift rocket to lift it. And its propulsion system is so puny that it can't go to low lunar orbit and get back out. So we're going to have to build a gateway space station just so that Orion has a place to go. And the whole architecture makes zero sense. The cost to launch one is about $4 billion. And we've spent, over 40 billion just to develop it. And those numbers just don't make sense to me. And I fought tooth and nail for years and years, both as an astronaut and then as a NASA administrator, to try and get them to fix it. And there was just too much corporate, control and people who really didn't think big picture to try and want to fix it. And so that's what we have. And it's disappointing to me because I think it's going to hamper our ability to go out and explore.
It sounds a
But
little.
we'll see. We'll
When
see.
you say that, it sounds unfixable. I mean, people, I just wrote something trying to go down the mainstream of what I feel is the Pied Piper effect with Elon Musk and Starship. We got ourselves in a bind here with a multi-billion-dollar government project by the US, and we got a Starship. And, I don't know if Elon can cough up the goods here. And what's your take on the private sector really bailing us out of this?
Well, first of all, private sector, Elon gets his money from the federal government.
That's right.
So it's not really private sector. It's just another contracting mechanism. Now he does put his own money and now he has lots of investors, but, NASA built SpaceX. We built it, we populated it. His vision, our money, and about a third of SpaceX employees are NASA and another third are Air Force. And then there's all those young people you see in the videos. And I have nothing but respect for it. They've done a great thing, but it took more money and took longer than had NASA decided to do that same job, with a small team of folks. That said, SpaceX is now its own company and is doing a lot of other stuff and launching, once a week, mostly Starlink satellites. That's going to make amateur astronomy truly annoying.
Yeah.
And actually, they're launching some at 8:22.
Yeah, we got
tonight,
a
aren't
flight
they?
tonight.
Oh, God,
Yeah.
it's 3 minutes, but that's okay. Watch it later.
I went out to see Comet Neowise on Lee Hill. And in the first, my eyes were getting.
Lee Hill is near Boulder,
Yeah, it's North Boulder.
Okay.
Yep, North Boulder. You can pop over Lee Hill and it's relatively dark. And I, pulled out a tripod out of the car and a small scope. I wanted to see Comet Neowise naked eye, which I did. But in the first 5 minutes, I saw a string of Starlink satellites before my eyes dark adapted enough to see a greenish comet. And that was, 4 years ago? Something like that. And, now there's more. It's a real problem and we haven't dealt with it. I will say that SpaceX Starlink folks have been working with the American Astronomical Society and a number of other groups to try and come up with ways to make them darker. So at least they're not naked eye visible, to make them, a little bit darker than 6 magnitude. But they're not there yet. And there's plans for 100,000 LEO satellites, all that will be visible with anybody's small telescope. So you'll have a constant stream of streaks. But anyway, you asked a different question, which is, can the private sector, I think we'll see, Blue Origin, is building the New Glenn, a real, orbital rocket. They've been building it for years. We still have no idea when they're going to launch. And if there'll be enough market. We have the launch market is saturated. There are more companies. I think at last count, there were something like 200 companies planning launch vehicles. And there's probably enough market 10 years from now for 8 or 10 companies in the launch market. So we'll see. I think as far as the lunar, SpaceX does have the contract for a lunar lander based on Starship. And we'll just have to see whether they can pull it off. I think it will take longer than they say. I finally heard NASA articulate in a briefing I got for SLS and Orion that the first lunar landing won't be before 2025. Up until recently, they were still saying 2024 because that's what the Trump administration said, and they didn't want to look bad. But there was, the Trump administration made no cogent plans to actually get a crew to the surface and back by 2024. It was all marketing. But, you know, we're days away from a SLS launch. It is a massive vehicle that will go around the moon if it's successful a number of times. We will do a crewed mission. And then the question is, how are we going to get down to the surface? And right now we're depending on SpaceX to do that. Now, in the meantime, we also have commercial landing program for science, where companies are building rather large, paid for by NASA in large part, NASA, to land on the moon with science payloads. And some of those companies may be able to evolve to a human scale lander. So we'll have to see. I think what you asked is, can the private sector rescue us? I really think, it's the public-private partnership or a different contracting mechanism. And I think what's great is that so many companies are excited about space and are willing to put their investors' money on the line to try and get into the space game and human space flight. I think it's very exciting. And many of those companies will succeed.
Thanks, John.
John,
Yeah.
just to kind of echo what you were just saying, what I was reading today on the internet is that Artemis 2 is currently scheduled for May 24. So that's kind of depressing, takes a lot of the excitement out of the Monday launch for me.
Well, keep in mind that, after the Apollo 1 fire, we went a couple of years before the next launch. So, which was a ground test. So even during, the golden age of Apollo, there was a fairly long time between launches, although once we got into it, we were launching pretty rapidly every few months.
Right.
But we don't have a, by the end of the decade requirement. So,
Right.
Yeah.
and at $4 billion a pop, we don't have the money. So, but anyway, for Leonard, my solution was to put the program on a diet, to reduce the weight. And then, things cost what they weigh, that we didn't need a really big capsule. I mean, the capsule is the least interesting part of the whole architecture. So if you went from a 5-meter capsule down to a 4-meter capsule and got rid of, a lot of the requirements that they had, that's just the transportation piece. You could have afforded a service module that would get you to low lunar orbit and a lander, and you wouldn't need a big rocket to lift it. You could use a Falcon 9. And that's the architecture we started with, that Administrator Nelson, then Senator Nelson. Well, there's a woman named Lori Garver, who was deputy administrator at the start of the Obama administration, and she wanted to cancel the whole thing. And so that's what Obama announced. And it was a lead balloon, because they didn't think about all the contractors in all 50 states and our colleagues around the world that were contributing to Constellation, who said, no, you're not going to cancel it. Congress decides what our space policy is, not the president. The president proposes, Congress disposes. So Congress said, no, we're going to do it. And then Congress designed the rocket, which is what we have now, the Senate launch system. And it's just a bad architecture. So we got what we got.
So does anyone else have any questions for John?
But in the meantime, hopefully we have a good launch. And in the meantime, James Webb is going to be out there discovering things, and Hubble, and we're working on the Nancy Grace Roman telescope, which is going to be an infrared survey telescope to study dark matter and dark energy. We have lots of, incredible planetary science missions. Europa Clipper is going to go to launch for Europa in 2024 and fly around and see if we can see if Europa is habitable. We may not find out if it has life, but we'll find out if it's habitable. We're going out to all kinds of near-Earth asteroids with Psyche and other missions, and we just finished the Planetary Science Decadal that I was a part of that recommends a really exciting program for planetary exploration going forward. So I think, the science part of NASA is really rocking. Thomas Zurbuchen is a great leader, and the team is just fantastic. So I'm pretty excited about NASA science, and hopefully we'll have a successful Artemis 1 launch, SLS Orion launch on Monday, and that mission is over a month long. So we'll have updates, pictures of the Earth or from a kind of lunar orbit, which will be very cool. And I think it will inspire people, and that's one of our goals.
So yeah, and I just want John, if you want to stay on, that's great. Leonard's going to do a little update. He does this every time of the international space missions. But I also wanted to mention that our next speaker will be Dan Durda, who on October 1st at 6:30. And John, you probably know Dan Durda.
Yep.
Okay. And he's going to talk about the DART. That'll be about 5 days after this mission hits an asteroid's moon. I think I've got this right. And he's going to talk about his science experiments and his work with the meteor crater. And he's done zero-G flights, and he and Alan Stern, who's also spoke to us in person a few years ago about Pluto, they both have flights on Virgin Galactic to go do suborbital experiments up there. So I just wanted to mention that to all our viewers here. And if you want to stay on, John, we'd love it. And Leonard, if we can make this work.
Yeah, I don't know if this is going to work.
We think it'll work.
We're in
Leonard
charge.
has an
That's
update.
the bad news.
But we always like to do, I don't know if you can see this, but we all are so appreciative of your talk here and opening up the universe for us. And we're clapping. If you don't see us, we're clapping. Yeah.
Well, thanks for your kind attention. And
yeah, thank you. This was one of the best. We've had a lot of over our 9 years existing here as the Coal Creek Canyon SkyWatchers. And we call it SkyWatchers because we want people who don't know a lot about astronomy to feel comfortable too. And I think you really did that for them, tonight. And yeah, so if you want to stay on, great. If you have to go, we understand. And then we'll see if we can make this work.
Make sure that plane is in good shape. That's all I care about.
Yeah, I'm not sure why you don't want to tell us what kind of plane it is, but that's okay.
It's an old X-15.
that's just a privacy thing. So
Yeah,
Okay.
yeah, okay.
Okay.
Well,
But if you
keep it
fly over Coal Creek Canyon,
yeah,
we
tip your
wanna
wings.
know. Yeah, tip your wings.
all righty.
Yeah,
Thanks all.
Thank you so much.
All righty.
Really, truly.
Thanks, John. We're still gonna hear from Larry.
So.
Okay, we're gonna try
you
to
gonna
do,
share screen.
and we'll see where we are
Wait,
here
I
with
think I
this,
have to
share
screen
something.
here too.
You're there. We see you.
Well,
Oh, God.
that's a good first, no, you don't want that.
Well, I
You
don't know.
still see that? Stop sharing. Do you want to continue? Yes. Okay. Uh-oh. We don't have John Williams here, so.
Barb, you're doing a great job.
You're getting better.
thank you. Oh.
How's that
Leonard has
look? Do we have
wait,
something on there?
Share. Okay, let's see.
We see the slides. Go back.
Okay,
Go back.
You were there.
Okay.
I was
I
there.
know. Well, we're both
Various.
working on our computers.
Do you have this set up for only 2 hours?
No, this is set up for eternity.
Yeah, the rest of our lives.
Let me get rid of this too. Okay,
Let me do this. Let me,
close that.
okay, close that.
That's right.
Okay, you're there.
It's
Okay,
there.
don't touch anything.
Okay.
Okay, we're
Now,
done.
Do you see it full screen?
That's all I have. It's just a date, and so you know what day it is.
So do you all see this? You see
Yes.
SkyWatchers?
Yes.
Oh my God. You know, I'm
Okay.
telling you, I could have had a heart attack earlier. No.
Now we're trying to get all this
John
together. Here we
Williams-
go.
Even, okay.
Well, we
but-
talked about
wait a
all
minute.
this. We're gonna
Okay.
get going here.
Yeah,
I don't want to be on here forever either. I
Yeah.
think you guys are
we'll
getting tired.
go fast.
But you know, here we are.
You're not full screen.
We're
We're
not
not-
full
oh,
screen.
no.
You need to go to the presentation icon down there on the bottom.
Uh-oh.
Go right, go right, go right.
Way over here.
See those 129% down there?
Oh, yeah.
Just next, that little thing to the left of it. To the left of the 129%. You're to the
Okay.
right of it now. You're getting there
How's that
right
go?
there.
Is that good?
Now we're good?
Looks like you hit 129.
Okay, well,
So wait, so he should go,
It's that little thing that looks like a podium right next to 120%.
wait a minute.
okay, wait.
Well, I don't know where.
Now
we are.
he's on that, what, don't touch everything.
Okay, here we
wait.
go. We're gonna do the
Um,
podium.
Did that work?
Why
It
don't you
didn't.
just go ahead with the presentation?
Yeah,
Yeah,
it didn't work.
No, wait, well,
Let me
okay.
see.
so, it says
Full screen.
120. So, oh wait, the podium, yeah, the podium thing. That's right there. I think. Right there, right
I
there.
got the podium.
No, okay. How's that? Does that work?
Didn't work.
Okay.
Did not work.
What do you see?
So let's,
Go back.
yeah, we're just
We
seeing,
can see fine. Let's go.
Now
Artemis
Roadmap.
Okay.
All right.
You do see that, but it's not full screen? Or you see the stuff at the top?
Full screen now.
Oh,
Um,
okay, so go to 100%, right?
I think-
Oh, how's that now?
It's good enough. Just keep going or you'll screw something up.
Yeah, you don't
Okay.
want to hear me too much, so
Yeah.
let's go
Just
back.
leave it and go.
Yeah, leave it and go.
Yeah, I can do this.
My whole life has
Oh.
been leave it and go.
And John Williams will be working with us in the future.
Yeah,
from
John is,
wherever he
you got to
is.
remember, John is leaving on Monday.
Yeah,
And
And-
he's been such a tremendous help on years of doing SkyWatchers. So we really salute him and we hope he lands on his feet out there. He
Yeah, well,
and Don.
yeah. he and his wife
Okay,
don't-
let
yeah,
me get
okay.
this going and get it over with.
No.
No, Artemis 1, we're ready. You know, John Grunsfeld, you know, talked about this. I mean, this is it. This is a big deal. And Monday is the projected launch date. I've got friends of mine that are there. They're sending me pictures. They're all excited. They're eating at restaurants. They're all ready to go.
We wish we were-
We wish we were there, but you know, I'm not a big fan of these first launches. They typically have problems, and
whether-
your hotel bill goes up continually because of delays. So while NASA has a sign that says we are going, it's like we are going when, you know, is always the problem. Next thing, okay. But it, you know, if it goes on Monday, it's a tremendous unpiloted, nobody on this thing.
well,
And it
we'll-
goes out pretty far, you know, past the moon and will come. The main thing that they're trying to get to, other than the launch and make sure the space launch system, you know, works, is to get this thing coming back to the Earth at 25,000 miles an hour. And the Orion capsule with the reentry shield, you know, they're going to try to test out everything, you know, about reentry into the Earth's atmosphere. So
with robots.
and
robots.
there'll be, you know, the whole point of this, you know, this is a big deal for NASA because we're rebooting the moon. And, you know, this is, you know, we're really getting back to where we were in 1972 the last humans to be on the moon, Jack Schmitt, Gene Cernan.
17.
So we're back to the moon. The Artemis program that's what it's called. And, you know, you need a logo with a shadow. So there it is. So NASA's already got a logo. Now you got to spend billions to make it happen. There are passengers on this spacecraft. They're all dummies. And what's really kind of cool about this flight is to take 3 different kind of mannequins that are loaded with sensors to understand radiation on a flight out beyond the moon and back, because this spacecraft is going to go out further than any other human capable spacecraft that we've ever launched. So it's a significant mission. It has a European Space Agency service module. They're a big part of this mission. So it's a big deal. This is going to be NASA's coming back big time in human spaceflight capability to the moon. They're already talking about Artemis 3, which is obviously the 3rd flight of this. The second one is the test of the Orion going around the moon with the crew. But the Artemis 3 landing is the first person of color, the first woman on the moon, is what NASA is billing this thing as. But the big thing in my mind is they selected 13 different locations where this lander may land. And it's in the South Pole region of the moon. And why are they going there? Well, because of these craters that have never seen sun for billions and billions of years. And within those craters, there appears to be lurking water ice that might be extracted to actually make a permanent base on the moon doable. And this is kind of a schematic of, what could be possible for a Artemis 3 future base camp. So, we're going back to the moon, and we're going to start slow, getting the rocket and the Orion capsule, off the ground and see how they work. And then we'll put humans in there, and then we'll expand the envelope more. Just recently, we had a briefing to our folks here on Capstone. This is a Westminster, Colorado group, Advanced Space, that has actually built this CubeSat, the Capstone CubeSat. It is now zooming in, and it is going to be, I look at my notes. It's going to be arriving in its orbit November 13th, 2022. And so that it was launched in June 28th. But anyway, it's doing its thing. It's going to be circling back to become a mission that will, again, nobody's on this. This is just a CubeSat that's very like a microwave oven. But it'll be in looking at an orbit that NASA wants to use for what may be, we're not sure, I'm not sure whether or not the Gateway space station will ever happen, but it could. And if so, this particular CubeSat is going to investigate that orbit and be very clever about what it's doing. Anyway, I just want to get back to China. As you know, and you're probably tired of me talking about it, keep an eye on China. They have this crew up there right now is busily waiting for the next module to be launched to their space station. They are in a situation, what looks to me like in the last week or so, there's too much radiation outside the space station to go out and do spacewalks. there's a solar storm going on, and I think they're waiting for it to be calmer, but we'll see them go out and prepare for the next module that's going to come to the Chinese space station. But this 3-person crew is busy. They're setting up a whole Chinese space station to get ready for a new module. And keep an eye on this. This is a big thing. This is the way it looks about right now. They launched a module. I think the last time we talked, I said they were going to. They launched the module on the left there, and it's docked with the complex that they've got in construction. And if everything goes well for the Chinese, they'll have their space station done, completed with another module by the end of the year. So that's an important development, and we'll see how they pull it off. However, we got a lot of stuff going on, and DART, we had several of the program manager people from NASA give a talk not too long ago about DART. And that's, we're right on the edge of having a DART interceptor asteroid planetary defense mission test, unmanned. This is robotic spacecraft that will hit the asteroid or a moonlet of a larger asteroid and try to move it. So this is our first planetary defense mission that NASA has pulled off. That's coming up. The impact is on September 26, 2022, coming up. And mark your calendars, 7:14 p.m. Eastern time.
And then Dan Durda.
And Dan Durda, our next speaker, will actually discuss what took place and what happened. So we're very excited about that. But this is a big thing coming up for NASA. Next thing, what goes up comes down. This is a bad news story. And I've been writing quite a bit about this. I've got a news story coming up a little bit on the edgy side, but we got a problem here. We got China launching these mega rockets to launch the next module. And if you remember, just a few weeks ago, we were paranoid about this rocket stage coming down willy-nilly, hitting the Earth. And this is a problem. I mean, China, it's not clear to me what they think they're doing here, but they are kind of like, well, it's okay. The Earth is 75% water. The chances of it landing on Earth are pretty nil. Well, it turned out it landed on Earth. And here's a picture of the reentry of this vehicle, a core stage, and it crashed in this area, and people picked up debris. And we got an issue here about regulations and who's doing what, launchings, and can we create some kind of capability, regulatory or whatever it's going to be, some kind of what do they call that? I just wrote about it. Demise. What is it called? Leftovers. I don't know. Anyway, there are techniques that we can use to build a spacecraft that can actually really demise in the atmosphere. Anyway, meanwhile, this guy in Australia wound up with a piece of space debris from a SpaceX launch landing in his farm. And that's how big it is. This was SpaceX leftover hardware. The guy on the right, this was another debris from years ago, but it shows you the kind of thing that we got to be starting to worry about here. More launches go up, more launches come down. And so I think we're not in a good position about reentry and some of the problems we're having. with hardware from spacecraft coming down and landing on Earth. At some point, somebody's going to get hurt. And I'm not even sure they haven't been hurt, because they probably haven't radioed in that, hey, I'm underneath a giant piece of nose cone. Anyway, we got some issues there to start working through. I think that's enough yelling for me. I'm tired. That's about it. And let's move on.
Yeah, and I'm just looking at the chats. Bob Graham said, and Van Allen probes renamed from radiation belt storm probe to honor still living discover.
That was from hours ago. Yeah.
Oh, sorry about that. Well,
Yeah. John mentioned 2 missions that had been named for people still alive, and that's the 3rd one.
Oh, okay. Yeah, good.
What mission was that one?
It's called radiation belt. I don't know, what did I call it?
Belt storm probe.
Yeah. So it's 2 spacecraft that are doing new work on the Van Allen belts.
Okay.
So Van Allen's like 91. They named the mission after him after it launched.
Yeah. Okay. Anyone with questions? We've kept you on here a long time, but I think this was one of our best. I mean, they're
Best
all
ever.
great.
Yeah, Barb, I did point out that the SpaceX launch has been delayed due to weather. So
good.
Oh, was it? Okay, so we didn't miss it.
No, it says 9:41 Mountain Time, but if you look at the video of the storms that are around there, it's kind of
Yeah.
what's going to happen.
What do you think? What do you think is going to happen
Monday.
for
Monday.
Artemis launch?
You know,
on
I
Monday?
was looking at those storms and going, boy, if they get those that day, it took 2 hits on the lightning deflectors or whatever they are today.
Yeah.
So yeah, I don't know. Good luck, guys.
Yeah, that's why we're here.
Yeah.
Well, and then Bob Grimm also said it's important to note that the crater rims and ridges are in almost perpetual sunlight, and that might have been
Shadow.
Shadow.
No.
Shadow.
No.
What?
They're
The
in
crater rims, it's the south pole of the
the
moon.
rim. Yeah.
Oh,
The
yeah.
crater rims and the ridges that they put those landing sites on
Yeah.
are next to the craters where it's dark.
Yeah.
But
Yeah.
those ridges and rims are in almost perpetual sunlight.
Is it looking?
Yeah.
Oh, okay.
Yeah.
And I guess they're, I think all those are aligned to the Earth so we can communicate.
Yeah, the Earth's, the Earth's axis is tilted. That's why we have seasons with respect to our orbital plane. But the moon, its axis is basically straight up and down with respect to the ecliptic. And so the moon, even if there was an atmosphere, it wouldn't have any seasons. So the Earth would always be, low in the sky, I guess. And, you can, I mean, depending on which side of a crater or other hill you're on, but, the Earth visibility direct Earth visibility is probably a constraint on those sites also.
Yeah. I think the other thing that people are not picking up on yet, these areas are exactly where China wants to go. This is an area where Russia wants to go. So I don't understand how crowded is it going to be with all these people landing robots and carrier craft with pilots. It's going to be a little.
Well, every one of those sites is, I don't know, 10 miles across or at least, maybe bigger.
Yeah. 10 miles. Okay.
Well, I heard here's a rumor that you can follow up on, Leonard. I was at a meeting and a NASA person said to me that the second CLIPS lander, the second robotic lander to the moon,
Yeah.
which is supposed to go to some northern place. Then it's supposed to go to Mare Crisium, not the mission that we're on. Now the administrator wants to send it to the South Pole ahead of the rest of the South Pole fleet so we can beat the Chinese.
Well, you know, it's a space race thing. I
It's
got
back.
some note from some guy from India. He said that's where our MIP lunar probe went down, and they hope that they could, the NASA folks could pick it up. So there's a lot of, you know, this is going to be a really territorial claimantship. We'll see.
Well, there'll be a charge for that.
Yeah, there'll be a charge.
Hey, Leonard, I think your joke of the Just Wait Space Telescope was beat when Grunsfeld called the SLS the Senate launch system.
Well, yeah.
I laughed so hard.
Yeah, I know.
Yeah, I love that because he doesn't mince any words.
Yeah, I was very impressed by his non-NASA view.
Yeah.
Well, yeah, the SLS, you know, the Space Launch System, the Senate Launch System, it's going to be a work. We'll see if it works.
Some people call it the pork lifter.
That's great.
Good.
So guys, just a few years ago, we ran into John at a Griffith Observatory, and we told him we had just been over to the California Science Center where they have one of the orbiters sitting there. And he had been there and he was just livid because they made it into an exhibit. He wanted it to be something that people could walk through and see where they worked, because that was where they worked. It was where they worked and lived. But he was mad because, and I think maybe understandably so, that it's been turned into this sort of sacred exhibit out there.
Yeah. Well, you know, we're going to see how this works. And I hope for NASA it goes well, because, I mean, the program kind of pins on it. But, you know, I'm just not I'm not on board, you know, Elon Musk and the, you know, the Starliner thing. You know, we'll see how he does. But, you know, on the other hand, he's proven me wrong. The guy's landing reentry first stages all the time is becoming like.
But why haven't they had a Starship tested forever?
Huh?
Why haven't they had a Starship tested so long?
I think because they figured their concept was feasible, at least.
Oh, they don't need to land them back in Texas anymore.
Well, you know, they got all these issues with the FAA as it is,
Oh, right.
and all the noise and all. So they showed that, you know, I think they were really uncertain if it would even work at all. And it took them, what, 3 or 4 tries?
Yeah, we got a ways to go with Elon. And, you know,
Yeah.
Well, I mean, his whole contract was like $3 billion, and SLS is $4 billion every launch, not counting all the sunk costs.
Yeah. Yeah. Now it's whatever it is, it's expensive, whatever angle we go. Yeah.
But you know, his statement that it was a puny propulsion system, I had never realized that service module that, you know, it's great we have this partnership with Europe, but it's solar powered. I don't know what it has for, you know, rockets, but it's not even enough to go into, you know, low lunar orbit.
Well, what I have heard is that rocket engine on the back of the service module is the equivalent of one of the OMS engines on the shuttle only.
Oh, geez, that says it all.
And the interim upper stage has like one RL-10, and they've been talking about developing the Righteous exploration upper stage, which would have 4 RL-10s, and they could, you know, launch huge payloads out to the planets with that. But I don't know when that's going to be ready.
You seem anxious.
Don't hold your breath, right?
Yeah. No, as I get older, it gets harder to hold my breath.
Yeah.
Yeah.
I hear you, especially at high altitude.
Yeah. Okay,
So,
I'm out of here.
Maybe oh God, I don't know how to do this. Okay, yeah. Yeah, anyone have any comments or questions or anything?
Well, I will comment that Leonard didn't bring up the fact that the Psyche mission has been postponed.
Oh,
I didn't do that. No.
yeah. Do you know about it?
Yeah.
Yeah. So how long?
Well, it's only going to be
I just
postponed
heard
by
today.
about a year, but it's going to have a different trajectory. So it's going to take like 5 years longer to get out there.
Tell everybody what the Psyche
Yeah, what
mission
it
is.
Okay, there's an asteroid called Psyche out there in the main belt that's probably made of mostly metal. And NASA's really curious about it. So they set up this mission. I think it's going to be launched by a Falcon 9 or a Falcon Heavy. But it was going to get a boost from the right slingshot from Mars to get out to the belt quicker. But now that's since they had a software issue that who knows when that's going to get fixed. It's not going to go for at least another year.
John, that also slows down another mission that was going to piggyback with it.
Okay.
I can't remember the name of it, but I just heard about it today from one of the guys at Martin.
Was that going to the asteroid belt too?
Yeah, and they're going to lose one of their targets, if not both of them. So
That's the
There's some-
little
yeah, you remember
simplex mission that's at a CU.
Yeah, and so they might get one target. They were supposed to have two.
Oh, yeah, it's software stuff. Well, that's what's been holding up Boeing for a good portion of their problems with all kinds of things like the Starliner and the 737 MAX and et cetera, et cetera.
Well, let's see. Oh God, I'm afraid to touch it. Okay. I guess we should stop recording, but I'm not sure how to do it. Let's see, stop it. Yep, let's do that. Are you sure you want to stop recording? Yes.